This is an example of a boundary value problem with the Dirac delta function. The problem goes like this. A uniform beam of length L carries a concentrated load W naught right at the middle. X is equal to 1/2 of L. The beam is embedded at both ends as shown in the figure below. We want to use Laplace transforms to determine the deflection y of x from this differential equation, where we have given conditions in the boundaries. We have the y, the position condition, and the derivative condition at 0, and then the position and derivative at the length of the beam L. So let's begin solving this differential equation using Laplace transforms. So using Laplace transforms, we want to take the Laplace transform of both sides. The EI is a constant, and the W naught is a constant, so that can be taken out. And so we take the Laplace transform of a fourth derivative of a function and the Laplace transform of the delta function. So here is a Laplace transform of the fourth derivative using this theorem, and we have the Laplace transform of the delta function using this theorem. So now that we have this equation, we put in our initial conditions. Now we have initial conditions for y of 0 and y prime of 0. That's given here. But we don't have initial conditions for y double prime and y triple prime. So what we're going to do with that is assign C1 and C2 some unknown constants. And then at the end, after we pull it back to the y of x world, and back to the real world, what we're going to do is we're going to try to solve for those constants by using the other initial conditions for the other boundary. So we take our equation, put in those values, the first initial conditions, the y of 0 and y prime of 0, and then we solve for y of s. So we divide both sides by s to the fourth, and then we break up into three terms, c1 over s cubed, c2 over s to the fourth, and then this other term with the constants and e to the negative 1/2 L times s over s to the fourth. Now we want this solution in the s world to go back to the y of x world, and so we need the inverse Laplace transform of that. So the inverse Laplace transform of y of s is simply y of x. Usually it would be t, but we're measuring our independent variable as an x. We're going to take advantage of this transformation from one of the theorems that we had, and so we need to transform the c1 over s cubed as something with a 2 in the numerator, as suggested by this transformation. And so we need to multiply top and bottom by 2 to keep it to keep the term unchanged. And then this has an s to the fourth power, which means we want a 3 factorial up on top, and so again 3 factorial in the bottom. And so we have the 2 over s to the third transform as x squared. The 3 factorial over s to the fourth transform as x cubed. So that was a little bit of the easy part. The other part is involved, has the shift, the Heaviside function involved. And so fortunately it's just one term. This is the one term that we're dealing with. We have an s to the fourth down in the bottom, and so again we want s cubed, so we have this matching up a transform of some function, and the function is going to be x cubed. but when we transform it back, inverse transform it back, that's going to be the x with a shift. So it'll be x minus the shift, which is 1/2 L. So it's x minus 1/2 L to the third power times the Heaviside function, the step function. So here is our solution. Now it would be nice if this was our solution and we'd be done. Unfortunately, we have to solve for that C1, C2, and for that we will need to take on the other boundary conditions. So the boundary conditions we have is y of L is equal to 0 and y prime of L is equal to 0. So that means we have to take our y function and take the derivative of that. Now the first two terms wouldn't be a problem, but this last term has the shift function, or the unit step function, the Heaviside function. So what we need to do, or one thing that we can do to make things a little bit easier for ourselves, is to temporarily substitute this and make it another function. Let's call it g. And then so our y of x is essentially going to be a simpler looking function, and now we just need to focus on g, because when we put in the boundary conditions L and take the derivative of that and put L in, this part is okay, and this part we'll have to deal with a little bit separately. So let's focus on g, the g function, the shift function. And for us to take advantage of that shift function, to take a look at it, what we're going to do is we're going to go back to the definition of the shift function. So here's our shift function, our g function. Defined as a piecewise function, it's going to be 0 from 0 to 1/2 L. That's where the shift happens. And then it's going to be that shifted function, that x cubed that's been shifted from x equals to 1/2 L on to the rest of infinity. So that's our g. Now if we put in L into that x, since L is bigger than 1/2 of L, then we're going to use this function L. And when we put L into that function, we essentially get L minus 1/2 L, which is just 1/2 L to the third power inside, and so that simplifies to 1/8 L cubed. So that's the g of L that we'll use. Now the derivative of g is g prime. The derivative of a piecewise function is the derivative of the individual pieces. So in this case we just take the derivative of the second function, that's 3x minus 1/2 L to the second power times the derivative of the inside, which is just 1. And so this is our new function, and if we put L into our new function, again we're going to use this function because L is bigger than 1/2 L. So L minus 1/2 L again is 1/2 L, so now we have 3 1/2 L squared, and that becomes 1/4 L squared times 3. So our g prime of L is 3/4 L squared. Now that we have those values, we put it back into our equation. We put the 1/8 L cubed and the 3/4 L squared in for g of L and g prime of L. And y of L, according to the boundary condition, is 0. Y prime of L is also 0. So we can take these terms and bring it to the other side, and now we have a system of linear equations in C1 and C2. Well, at this point there are several ways to solve for this. One way is to isolate C1 on one side and then make the substitution C1 over here and solve for C2 and then go back to C1. But we've used at one point we've used Cramer's rule, so we'll use Cramer's rule, and assuming that we have a matrix of coefficients and then we have our solution set that we want to find. Here's how we're going to apply Cramer's rule. C1 will essentially be this matrix with the solution on the other side of the equal sign to be the first row or the first column in our matrix, and we want to find the determinant of that. So the determinant is diagonals minus the wings, and so here are the diagonals minus the wings, and then the same for the determinant of our original matrix, diagonals minus the wings, and then we got it to simplify to this. So this is C1. Likewise for C2, we take our original matrix, and then in the second column we're going to replace it with the other side of the equal sign, and then do the same determinant calculation, and then now we have our solution for C2. Okay. Now that we have C1 and C2, we replace C1 and C2 with the values that we got, and we're going to put this original version, instead of the g of x, we'll just put this back because that's our original answer. And upon simplifying this, we finally get our solution, which is W naught L over 16 EI times x squared minus W naught over 12 EI times x cubed plus this W naught over 6 EI times that shifted x cubed function. Okay, so this is our solution for our problem.